So you've probably seen a lot of levitating motors by now, but I bet this one might amuse you, although I'm hoping for a bit of a mind-blowing action here and there. So here's my invitation to you to watch the story of me building mostly useless but fascinating levitating motor of my own design, controlled by a microcontroller, with a detailed review of its functions. Spoiler alert, I ended up building 3 different models eventually, but I'll get to that further on. Welcome to Soulful Crafts. So when I first saw one of these levitating motors, the first thought that popped in my head was,
"Can I have 2 of these wrapped up and sent to me, please?"
Come on, it has magnets, it levitates, and it spins without any external power source, what's not to like? So the first pretty much simple checkpoint was building this fella. The design is very simple and easy to replicate. If you're interested, here's a drawing with all the dimensions and instructions on how to make one. Sure, it's easier and cheaper to buy one online, but where's the fun in that? Well, despite this simple levitating motor being cool and all that, it got boring real fast. See, I've done a sloppy job balancing the rotor, so it wouldn't start itself when under a direct sunlight, and was bad at maintaining rotation in dim lighting conditions. So it got me thinking, what if I could build a motor that would spin reliably in any lighting conditions, could be started and stopped on demand, and would be fully autonomous? Oh, did you hear someone shout out "Free energy" just now? Or is it just me? Well, I'll address the autonomous part a bit later. So eventually I've built this new, much more complex in design motor that was driven by a microcontroller that controlled its rotation, measured rotation speed, detected if the rotor had stopped, and restarted the motor if was needed. And when it was dark around, it spun the rotor compulsorily using infrared spectrum LEDs, the same ones you would find in any TV remote control. Their wavelength is invisible to human eyes, so it was a pretty neat solution. But this design was flawed in many ways. The main problem was with the body design of this motor. I didn't account for the fact that the motor will be living on the window ledge, where the air temperature varies drastically with the change of the seasons. It's freakishly cold in winter and unbearably hot in the summer, hence the thermal expansion and shrinkage of the body frame resulting in changes in magnetic field of stationary magnets, rendering the whole device useless. So come spring or winter I had to adjust the configuration of the rotor in order for it to spin properly. And the second major flaw was that the motor became even less autonomous in comparison to the previous model, since it was powered by lithium battery now, which had to be charged obviously. But I'll address that later, as promised. So one day I've had it with this model and decided to spice it up a notch with blackjack and a better body and rotor design. And I tossed the blackjack idea eventually. So for my final model I decided to redesign the body in such way for it to become much more rigid and unsusceptible to temperature fluctuation. Also, the new design allowed for the filling to be located inside the body, giving the device a more aesthetic look. At least in my eyes. I modified the rotor as well. Previously it had 2 windings and respectively 4 solar elements. Now it has 4 separate windings and 8 solar elements, which made starting the motor in the absence of sunlight a much more simple task. The rotor is made out of a brass tube with a mounted ball bearing at one end. On the corresponding part of the motor's body I've installed a piece of glass, which I cut from a larger sheet, so I used only a small piece of a whole sheet. Also, there are 2 support magnets located on the rotor shaft and a sort of an encoder disc, which allows measuring the rotation speed of the rotor, detecting the rotation direction, or any movement for that matter. For this purpose I decided to use 3 Hall effect sensors spaced 120 degrees apart, with the magnetic encoder spinning inside. As you can see, the encoder has 4 magnets placed in square shape, although only one of them affects the Hall effect sensors. The rest are there as counterweights and are facing the sensors with an opposite pole, having no effect on the sensors. Here, I'll show you what I'm talking about. I'll set up an improvised testing stand using the same Hall effect sensors that are used in this motor. As you can see, when the sensor is in the idle state, its output is high and the LED is turned off, since there is no current flowing through it. But in the presence of a magnetic field, the sensor's output goes low, allowing the current to flow through the LED. Although if I reverse the polarity of the magnet, it has no effect on the sensor's output and the LED stays off. Keeping that in mind, all that's left is to write a simple logical level change interrupt event handler for the microcontroller, and we've got ourselves a tool to measure the rotation speed and whatnot. Speaking of the microcontroller, I've used an Atmega 328P for this project. It's the same chip you would find in an Arduino board, but without the bulky board. Yeah, the bare chip doesn't have that plug-and-play capability that Arduino has, but it allows making more compact and custom devices such as this one. Okay, I think we've got to the part where it's time to address the autonomy of this device. Well, the initial plan was to create a device that doesn't need to be plugged into the power outlet, which is a difficult task considering the fact that it's being powered with a lithium battery. The total capacity of the battery is 6K mAh, which allows the motor to work continuously for about 4 or 5 days, depending on how sunny the weather is and for how long I allow it to spin when it's after dark. And I'm charging it using a DIY solar panel that I made especially for this motor. Talk about dedication, huh? But it's alright, I'm not insane, my mother had me tested in childhood. After all, a man should have a hobby, right? Right? Anyways, I'll describe this solar panel in detail in my next video, which will see the light of day shortly after this video. So if you're interested in this topic, stay tuned for that one, where I'll also explain how I'm harvesting spare energy that's left after charging the motor. Okay, let's get back on track. As I mentioned previously, this motor is able to run even in total darkness, thanks to the infrared spectrum LEDs. Here you can see how it automatically starts itself in extremely dim lighting, after detecting that the rotor was stopped. It's so dim that you can even see potato-ish trails from my camera. Now let's take a look at the software capabilities a bit closer. I wanted to keep the interface simple and clean, so the control panel has only two buttons: the menu button and the page/OK button. The standby screen depicts the following information: the revolutions counted from the first power on. Oh yes, all data is stored in EEPROM and isn't lost when the device is turned off. An icon that indicates if the rotor is supposed to be spinning or not. The number of days of continuous work without power off. The clock. Current rotation speed. A box that indicates current work mode. And a battery charge indicator with a little log depicted on it. I'll explain it later on. Pressing the page button allows you to scroll through various statistics screens. The first one shows you the maximum values for the counted revolutions per day as follows: for today, in 7 days, in 30 days, in 60 days, and an absolute maximum registered. The next page shows the maximum values for the rotation speed registered, with the same statistics periods as the previous page. You can see that the absolute maximum rotation speed that has been registered for now is 1.3K revolutions per minute. It's a little faster than an average washing machine in a spin mode. The next page shows the number of rotor stops for today. It usually is a 0, but I had to stop it several times while preparing to record this video. And the last page shows the number of assisted rotation cycles for today. The assisted rotation occurs mostly during morning hours when it's still dark, and in the evening when it's already dark. It has two counters, one for successful cycles, where the desired speed was matched, and one for unsuccessful cycles, where the cycle was automatically aborted without reaching the desired speed, which is hard-coded to 200 revolutions per minute. But the second counter always stays at 0, cause I made it for debugging hardware issues that were dealt with. And I'm too lazy to change the code once again. Also, reflashing the software will cost me all the collected statistics. So let it be as it is, I say. Now let's explore the other button. By pressing the menu button, we get to the menu, pretty much self-explanatory. While we're in the menu, pressing the menu button scrolls through the menu items, and the well-known page button acts as a confirmation button. So the menu contents are as follows: stop or start the motor. It actually changes depending on the current motor state. Delete all data. I had to make an additional "Are you sure" page, don't ask me why. Turn off or on the battery discharge protection. If this item is on, the motor will go in hibernation mode when the battery charge reaches 30%, until it detects sufficient battery charge to continue normal operation. But this menu item is mostly hereditary from a previous model, because now it automatically starts charging when reaching 35% limit. I've added this feature in order to exercise the batteries so that they wouldn't stay fully charged all the time. What are your thoughts on that? This allows a charging cycle without reaching the minimal battery voltage. This sets the minimal rotation speed where the rotor can still spin on its own. Any reading that is below this setting will trigger an assisted rotation cycle. This is a clock setting item, which allows, well, to set the clock. turn off or on the work and shifts mode. This item allows to set the desired time for the motor to start rotating and to stop rotating. I have this set up so it starts rotating at 8 AM and stops rotating at 11 PM, regardless of the lighting conditions outside. And there is the exit the menu item, and the last one is exit the menu and turn off the display, because otherwise the display stays on for 60 seconds since the last press of a button. In conclusion, I must say that while editing this video, one thought ran through my mind. Maybe, just maybe, I got a little carried away while making this motor, and it really is extremely over-engineered. But hey, making things like that brings me pleasure, so I consider time spent on building this device well spent. Would definitely do it again, but next time with blackjack and Wi-Fi. If something was left out in this video that you're interested in, feel free to ask about it in the comments. I'll be glad to answer your questions. Hope that this video was of any value to you. If you like this video, please consider liking or subscribing. Or liking and subscribing. And if you didn't like this video, you can share it with the person that annoys you, just to annoy them. Thanks for watching, take care, see you next time.